So the next presenter will be James Bonnet from VICTREX, and his presentation is entitled How New Magnet Wire with PEEK Polymer Coating Can Improve Electric Powertrain Performance. And please, James, the floor is yours.
Okay, thank you, Professor Cavallini. Good morning to everybody. So let me share my screen and check. We don't have any more IT problems. I think you can see the screen now.
Yeah.
Professor Cavallini, is it correct?
Yeah, we can.
Great, thank you. So I guess a short introduction. My name is James Bonnet. I am the e-mobility program leader at VICTREX, and I've been researching different types of PEEK applications in electric motors and other powertrain systems for the last 7 to 8 years. And as Professor Cavallini says, I'm going to be talking you through today a design investigation piece of work that we had commissioned at VICTREX about how new magnet wire with our PEEK polymer coating can improve the electric powertrain performance. So first of all, I'm just going to quickly introduce the company, VICTREX, and PEEK Polymer. Then there's one slide on vehicle electrification, which covers trends, technology trends and the enablers. Another slide that follows that will look at a quick comparison of different magnet wire products. And then the bulk of the presentation will be reviewing the case studies that we've had commissioned. Then they're using both simulation software tools as well as hardware electrical stators that were built and measured test results from those hardware results. Okay, so we have limited amount of time today, so I will only be giving quite a high level overview of the company. But if people have more detailed questions, we can get to those in the chat or perhaps one-on-one by email after the presentation. So let's get started then. VICTREX as a company was born out of Imperial Chemical Industries, ICI, quite a well-known British chemical manufacturer. And our chemists were actually the original people who invented PEEK polymer. So we have a pure PEEK polymer focus at VICTREX, not like many other chemical producers where we have a catalogue of many different polymers in our portfolio. And it does have some benefits because it means that we have the largest nameplate capacity, and we also have a team of over 800 people waking up every morning thinking about how to solve our customers' engineering challenges in the context of PEEK parts and PEEK product forms. We have 6 strategic markets which we focus on with a rich history of many firsts, examples of metal replacement within certain different markets. And whilst we are obviously very reactive to solve our customers' problems when they approach us, we're also quite proactive in that we have many collaborations across industries, and we've made various investments when some markets and supply chains are not ready to have PEEK polymer solutions because of things like product availability, because of risk mitigation, or some other specific reason. Having said that, though, we make many alternative PEEK product forms, for example, PEEK films or filaments that are used for 3D printing, different types of pipes made from PEEK, and composite products as well, composite tapes, to name but a few. As well as these PEEK product forms, we even design and manufacture some specific parts where there is a strategic market need there. I guess this gives you all a glimpse of how VICTREX is in fact a little different from traditional resin suppliers, and how we like to focus on customer collaboration that creates value. Perhaps important to note that our business model for magnet wire is not to move into magnet wire manufacturing. Instead, we work with partners and we supply our resin to those experts in magnet wire manufacturing who are best placed to answer the industry needs. So for those of you who are not familiar with PEEK or polymers in general, this slide should give you a little bit of context. So on the bottom right, we have the polymer pyramid here, which represents how different types of plastics have different technical limitations or performance windows. And they're manufactured at different scales as well. Subsequently, there's different pricing levels. So as we move up the vertical axis of the polymers generally increase in their performance window and their capabilities, but likewise the cost of that polymer would increase. And generally speaking, that's because, you know, there's not very much of it manufactured. So at the bottom we have huge volumes manufactured globally, and at the top very much smaller volumes. For example, polyethylene, a widely used plastic, it's classed as a commodity polymer, and the annual global capacity for this type of polymer is in excess of 100 million tons, in contrast to some of the high performance polymers at the top, like PEEK, which have an annual global capacity of less than 10,000 tons. So on the top right, the properties descriptor, it looks at some of the unique combination of properties that PEEK can have. And as a general rule, PEEK is not a polymer with one single property that's better than all the other polymers in that field. But it's usually, we find commercial success when the application has a need of combining demanding requirements. So if we take e-motor insulation components as an example, whilst PEEK doesn't have the best dielectric constant as some polymers, like a fluoropolymer, it's the combination of the electrical properties with the mechanical strength and the extreme temperatures that make it a good option for electric machine insulation components. Perhaps some of these other properties as well, like chemical resistance and resistance to hydrolysis are positive, but it's this combination factor that leads to commercialization and commercial success in applications. So we've just recently launched a family of PEEK polymers called VICTREX XPI. This stands for Extra Performance Insulation. And these family of polymers, they're designed to meet the needs of both the processors who manufacture the magnet wire, as well as the electric machine manufacturers and the other end users. So the next slide links how our new XPI grades can be used as magnet wire insulation that helps meet some of tomorrow's e-motor design challenges. So let's have a look at some of those technology trends and challenges. On the left-hand side, we've highlighted several technical trends for electrified vehicle powertrains that are linked to increasing the power or energy density of the components within the powertrain. Another key trend is around improving efficiency of the system, and this is usually done through optimizing thermal management. Finally, another trend that we believe is very pertinent at the minute is the increasing system voltage that are used in electric motors. These technology trends enable improvements in the vehicles themselves. And that's really important for consumer acceptance and improving consumer experience when they drive battery electric vehicles. The couple of examples we called out here around increasing the charging speeds for when the vehicle has come to the end of its electrical stored life, but particularly when we think about long journeys on motorways. And faster charging is very important. Also, another enabler here that we've highlighted is the faster switching technology. This happens in the inverter, and it will usually create a significant efficiency saving in the power electronics that can increase the vehicle range or could actually reduce the cost of the vehicle overall. All these technical trends and enablers contribute to equipment manufacturers' objective to improve certain factors around range and cost, charging speed, and driver experience, to make vehicles more attractive for consumers and to mitigate the perceived risks of buying vehicles with what is essentially a new technology. The faster that these factors can be improved, the quicker battery electric vehicles will become mainstream and lay the path back to profitable OEM vehicle portfolios. So my next slide is a comparison of the different types of magnet wire products. And the table that you see is designed to give a qualitative comparison of the different groups of magnet wire products available to e-motor designers. It's by no way meant to be exhaustative, and it represents VICTREX's own internal assessment based on our inquiries and based on our experience with tier 1 and 2 suppliers, as well as OEMs. I think the key message from this table is that VICTREX XPI as a magnet wire coating can potentially solve more of the demanding requirements in high voltage performance electric motors. But what we did is we classified the products into 3 groups, as you can see on the vertical axis in the columns. Firstly, enamel. So this is manufactured in a continuous manufacturing process. It's not fusing glass powder or paint, as the name suggests, but it actually uses polymers dissolved in solution, and they are dipped and run through dyes before having the solvent baked off, and then repeating this multiple passes to build up a layer of coating thickness. Typically, it comprises of 2 or 3 different materials, such as modified polyester chemistries, polyamide-imide, and then polyimide in higher specification derivatives. These products have been used for well over 75 years and are mature and well known in the industry. The next column looks at a different category, taped polyimide. So this is a wire wrapping process that uses high performance, very thin polyimide films that are modified and sometimes combined with other materials to support the process of gluing the different layers together, or overlaps as they are created with the narrow width tapes as they're wrapped around the conductor. Again, these products are quite mature, have been widely used for the last 25 years plus as magnet wire products. And the third column on the right hand side is a type of magnet wire you may not be quite so familiar with. So this, we use VICTREX XPI PEEK polymer in a melt extrusion manufacturing process where it's coated, the polymer's coated, sorry, and it's heated up in a large sort of hot screw, and then the polymer is squeezed through a die to control the shape and the thickness before coated onto the wire in one single layer of coating. The extrusion, it's probably only begun being recently used in the last 5 years, and is more of a new product in this industry, in a new manufacturing process, which means the supply chain is limited today. So what I want you to take away from this table is that VICTREX XPI coatings, when extruded onto wires, can have advantages, specifically in the maximum coating thickness that's available. This is really important for higher voltage systems. Also advantages in thermal classification and thermal endurance, and also in reducing the number of faults per length. As most modern automotive manufacturing processes move towards 0 defects, any products that are offering improvement here are usually well received. Perhaps the only other area that we might want to highlight is ductility, as this again is another area of benefit because of some novel machine winding technologies and more dense winding heads or more high power density motors are being designed these days. So now if we move on to look at we investigated the potential improvements VICTREX XPI coatings can offer. We couldn't do that on our own. We needed specialist help at VICTREX. So we approached eDrive Engineering, a consultant based in the UK, to support our design investigation into hairpin wound motors that were typically used in electric vehicles. We asked them to identify a high voltage motor currently used in vehicles and then investigate if this model of motor could be improved using VICTREX XPI coated wires as part of that insulation system. So here's what they came up with. Firstly, they identified REMI's high voltage hairpin motors that were used in several BMW hybrids and other equipment manufacturers' vehicles, as well as some commercial trucks. This motor that they identified was a permanent magnet synchronous machine with hairpin windings, and the system was designed for direct oil cooling of the end windings. The current winding design of this motor used is a distributed principle. That means that more than one phase is contained within the electrical stator. You can see here in this cross section, these two conductors are of the same phase, but these two conductors down here are of a different phase. And that's quite important because it creates a more demanding electrical insulation needs. Next, eDrive sourced the REMI motor for us and made a teardown of that motor. You can see some of the pictures here shown on screen, but what the guys did was built a full CAD model that can be imported into various different simulation software to model electric motor performance. And finally, eDrive presented several different insulation options to us where they were replacing the enamel wire coatings that you can see here by the sort of red colouring on the wire. They replaced these enamel coatings with VICTREX XPI. And the details of one of these designs that they put forward will be explained in the next few slides. So let's move on to those slides now. So the design which was selected to move forward with more detailed simulation and also hardware testing is shown on the left-hand side of the two graphics. So the graphic on the left-hand side is the original REMI high voltage hairpin section of the conductors, the two different pairs of phases, along with the slot liner that is used and shown in blue in an S shape, where the wire coating is a conventional enamel around a 70-75 micron in thickness, and it's shown in amber and blue. The right-hand side shows the modified design. Again, the slot liner is still shown in the S-shaped configuration in light blue, and the conductor coating you can see has increased is shown in amber. But this is a conductor coating material that is VICTREX XPI, our PEEK polymer. So when designing the insulation materials and the geometries that are required for a type 1 or a partial discharge free electric motor, the most demanding insulation requirement occurs between these two phases here of supply for this given winding design. eDrive highlighted to us that because of the greater partial discharge inception voltage that's created by having pairs of conductors so close together, that coating them with VICTREX XPI in this right-hand example, it enables a much thinner slot liner to be used while still maintaining the minimum electrical insulation that's required. The engineers at eDrive also then proposed to use this free space in the slot to use that space and increase the conductor, the copper conductor size. So therefore, by using alternative slot liner design and a larger conductor size, along with a thicker XPI wire insulation, this resulted in potential reduction in the total thermal resistance, as well as the overall electrical resistance, which has potential to improve the motor efficiency and the torque density. You can see at the bottom right of the slide how the insulation coating thickness is calculated, and that's, we'll explain that a little bit further in the next slide. So let's move on to that slide here. So according to the IEC standard referenced in the title, for a type 1 or a partial discharge free electric motor, the calculated PDIV must be done so using the DC bus voltage, the designated stress category, the selected safety factor, and then the predicted thermal endurance of the insulation system. These factors are defined by the rise time created by the inverters that govern the size and the frequency of the alternating current sent to the machine. The greater the voltage levels and the rate of switching between positive and negative, they require a greater, they give a greater electrical field intensity and thus require better insulation. The most critical point for the insulation to handle these stresses is in a distributed wound configuration, is that phase-to-phase value of PDIV that I showed on the previous slide between the two pairs. So PDIV is affected by pressure, humidity, temperature, but after these environmental factors, the number is driven by physical separation of the conductors, so the distance apart, and the relative permittivity of the dielectric material between the two conductors. In our scenario, though, this isn't just one material, it's several materials combined. It's the wire insulation, the insulation paper, and the impregnation resin. So as you can see in the first, the XPI coating is contributing to much more proportionally than the enamel. But you can see if I flick forward to the second graph, there is a thickness saving here in those overall materials, and that's what enables the increase in copper density that is ultimately one of the main contributors to the benefits that's laid out later in the presentation. So before we look at those detailed benefits in the motor, I wanted to share with you some actual wire testing data made on samples. You can see in the pictures and images what these samples look like. They're called back-to-back pair wire tests. And on the x-axis, we have the thickness of the insulation here. And on the y-axis, we have the measured peak-to-peak values for the inception of partial discharge according to this IEC standard here. So whilst the PDIV values, they can be calculated according to various accepted scientific paradigms, because of the enamel coatings are usually made of more than one material, it's difficult to predict exactly the PDIV, because it also depends on manufacturing quality as well. So we thought for best accuracy, it's best to take measured test data. And you can see from the test data we measured, for the same thickness of coating materials, we have enamel down here in the light blue, and the XPI coating in the dark blue, there's about a 10% improvement for a given thickness. We were unable to find any commercially available enamel coatings with thicker thicknesses, but at least on this graph you can see how the relationship with PDIV changes with increase in thickness. So let's now look at the next chapter of our presentation, which is seeing how the results of the simulation models, where we chose one enamel control experiment and the modified insulation design using XPI coating. Let's see how those transpired or transferred into electric machine benefits. So if we look at two different types of cooling system, which the eDrive engineers could do in their simulation model, we found that in oil-cooled motors, there was a 19% reduction in the end winding temperatures, which eDrive engineers were confident could mean that we could realize an increased normalized torque benefit, the continuous torque, of around 12%. In the second design, the eDrive engineers had modeled a water cooling system, which uses a water cooling jacket on the outside and draws the heat out through the electrical steel. In this model, the benefits were even greater simulated. They simulated a 45 degrees C reduction in end winding temperatures, and that would translate to an increased normalized continuous torque of around 17%. So we discussed this simulation of the electric motor performance benefits, but we thought it's also important to understand how the OEMs would use these types of improved motors in their vehicles. Our supplier eDrive offered some further options based on their advanced simulation tools that would allow them to predict the impact of using such a motor in a battery electric vehicle. So what we did was we took the efficiency model of the motors and we modeled that across the WLTC Class 3B drive cycle using a Jaguar I-Pace vehicle. All the I-Pace assumptions required are available in the public domain, as is the WLTC drive cycle. Once we have the efficiency map, that enables us to make this vehicle forecast. The only modification we had to do was to increase the axial length of the machine to scale it to the I-Pace motor requirements. So you can see here the different assumptions we have to take about the vehicle, but what we found was when we ran our improved XPI coated wire motor through this class test, we found that the energy consumed was reduced from the enamel model by 2%. And based on the map, the vehicle statistics, 2% is quite a significant number when we think about what that means for vehicle range. So what we're doing here is looking at if we take the assumption that all the energy that's saved from having a lower loss electric machine with XPI coating can be used back into traction and drive force, with 2% energy saving, we can actually increase the range of that vehicle by up to 10 kilometers. Another way to look at this benefit could be to achieve the same range, but to reduce the overall battery capacity. The I-Pace has about an 85 kilowatt hour capacity, and based on reducing that by 2%, there's a significant over $200 worth of cost savings here that could be a potential benefit for the OEM. So that comes to the end of the simulated work that we had done, and now what I wanted to share on the last couple of slides is some of the electrical stators that were built and what our actual hardware measured results were, so that we can compare those to the simulated results. And in summary, the thermal results that were measured by the stator hardware that was built, they matched pretty much exactly the data that was predicted in the simulation studies and this was, I should mention, the hardware piece that we built was the electric motor, the electric stator, sorry, in a water-cooled jacket. The other important conclusion or the important observation that we saw from this hardware testing was that the electrical measurement results were better than modeled in the simulation. So in our simulation, we designed the electrical insulation system to basically have parity. So the enamel and stator and the enamel and the slot liner and the impregnation resin were designed to be the same as the thicker PEEK with a thinner slot liner and similar impregnation resin. And we've actually measured a 26% better partial discharge inception voltage value for those two different stators, which is very significant, but pleasantly surprising. So I have got more details around how those tests were done, but just looking at the time, I think in the interest of time, I should skip to the summary and let any of the participants ask some questions, Professor Cavallini. So in summary, we've launched a new product family of PEEK polymer called VICTREX XPI for use in magnet wire applications, and we see the benefits here can be around enhancing motor efficiency, increasing vehicle range, reducing battery cost, and improving thermal management. So here you can see my contact details, and I think I'll stop sharing the screen now.